Welcome everybody to this AI and obesity prevention, leveraging technology to address obesity. This is the first webinar, which is organized in the context of OBEClust, which is a cluster of European Union funded projects on obesity research, prevention and treatment. So I'm Paulo Oliveira. I'm chairing this cluster. I'm also the coordinator of one of the projects in the cluster called GRAS. So I'd like to first acknowledge everybody that was in the organization of this webinar, which started by an idea of the communication and dissemination work group in OBEClust. OBEClust has different work groups on different topics, and several are very, very active. This is one of them. So this communication and dissemination work group has been doing a fantastic job in promoting OBEClust initiatives and organizing them as well. So for those who actually have no idea what I'm talking about when I mention OBEClust, this is an European research initiative that was launched in 2023 and to address the obesity crisis throughout a collaborative network of different EU-funded projects. So there's a total of about 80 million euros funded, of course, most part or largest part from the European Union, but also a smaller part from the UK Research and Innovation and Switzerland State Secretariat for Education, Research and Innovation. So this makes the whole 80 million euros. OBEClust unites researchers, clinicians, non-academic individuals, companies, and so on, to develop interventions, ideas for obesity prevention and treatment across Europe. So we're talking about, like I said, not only going from identifying, for example, molecular mechanisms that lead to obesity, but also develop literacy tools, ways to follow up what is the incidence and prevalence of obesity, to prevent, to treat. So it's a very large scope of activities, and the impact, the joint impact is actually much larger than the sum of the individual projects. So just to mention the 9 projects that are part of OBEClust, we have OBELISC, we have GRAS, Biostreams, eProbes, Better for You, Healthy 8, Shift to Health, OBCT, and Co-Diet. So those 8 projects, they have common topics. For example, identifying the risk for obesity. The risk factors for obesity is common to most of them, but then each one of them has the particular topics that are under study. So this is one of the objectives of OBEClust, is to pool resources, align methodologies, to create solutions that cause impact, that are scalable to different countries in the European Union in order to improve the health outcomes in the different target populations. So, and again, none of those listed projects can create the same impact as the 9 combined. So I'd like to before we start with our talks, first to thank again the organizers, to thank the speakers. So we have an excellent panel of speakers. Also thank the European Commission, because they actually were the spark and the funding. They brought the vast majority of funding for the 9 projects. So we have to acknowledge them, and also to acknowledge the project officer Marina Constantana, because she was actually the spark behind us joining together, and she's been active in trying to make sure that all projects run smoothly and together as one, basically. So after this introduction on what OBEClust means and is, I would like to start with our first speaker, and I hope she's online, right? Jennifer Baker.
Yes, no? Hi everybody, here is Galero Disperati from Martel, which is one of the partners in the projects. No, actually, Jennifer sent a recorded presentation, which I'm going to share with everybody.
Okay.
In a second.
Sure, yeah. Sure. So I'll just introduce each speaker. So there is a limited time for each one, of 10 or 20 if you have 2 speakers. And at the end, then we open a session of questions and answers. So I invite all the participants that are online, and I see we have 85 combined also with the speakers and organizers, which is an excellent number, to ask questions so we can have an interactive conversation. So Jennifer is not here, but I can tell you she's the head of Lifecourse Epidemiology at the Center for Clinical Research and Prevention at the Copenhagen University Hospital in Bispebjerg and Frederiksberg in Denmark. Jennifer Baker is the president-elect of the European Association for the Study of Obesity, EASO, so a very important partner in all of those projects. So EASO, for those who don't know, is a federation of professional membership associations from 38 European countries and also partner in several of the OBEClust projects, and this includes Obesity, Better for You, and Biostreams. So you can start the presentation.
Thanks. It will just play in a minute. I think it's visible on screen for everybody.
Yes, correct.
And I will remind that for the questions, for the Q&A that you mentioned, the Q&A box is open to all participants. Thanks again.
Thank you.
Hi, I'm Dr. Jennifer Baker. I'm the head of Lifecourse Epidemiology at the Center for Clinical Research and Prevention in Denmark, and I'm also the president-elect for the European Association for the Study of Obesity. It's my great pleasure to be here today to share with you about artificial intelligence in obesity treatment, opportunities, and challenges. In terms of declarations, I engage in educational and advisory board activities with Novo Nordisk, but I have no conflicts of interest with regards to this presentation today. So artificial intelligence, AI, what is it? It's all around us already. These are a series of technologies that enable computers and machines to simulate human learning. This is in terms of comprehension, problem solving, decision making, creativity, and even autonomy. Within this series of technologies, there's subsets, and a really key one in the area of obesity research is machine learning. So this is a technology that enables systems to learn from data and improve performance without being explicitly programmed. Furthermore, another subset of machine learning is called deep learning. Now this technology uses artificial neural networks that simulate how the brain works to model complex data. Advances are all around us and ongoing, so it's a really exciting time in this field. With regards to obesity, how is AI working? Well, AI depends upon big data. Data sets which are larger than we could have comprehended even 20 years ago. Big data are the food for artificial intelligence. They feed into the systems of AI, some of which are obvious, some of which are more unclear or black boxes, we would say, and from all of these processes, we gain predictive signals. In our case, this would be predictive signals for how to better prevent, treat, and manage the disease of obesity. And the key about these predictive signals is we use them to gain actionable insights. AI is already being used in obesity medical practice in a variety of different ways. These range from medical education modules, chatbots for charting and note-taking, medical imaging analyses, disease diagnosis and basic medical advice, and excitingly is being used more in the area of precision medicine and personalized recommendations. But all of these factors depend heavily on predictive analytics, and this is where we're going to focus for the rest of the talk today. So, what are big data in obesity? According to definitions, they are always digital, they have a large sample size, and a large volume or variety or velocity of variables that require additional computing power. So it's really coming down to this volume, variety, and velocity. We're focusing a lot on data today because this is the food for AI. When we think about data, there's two major categories. One is called design data, and these are collected and created for a purpose. Examples of this include cohort studies, randomized clinical trials, administrative databases. In contrast, we also have organic data. So these are generated through processes not designed for research. Examples of this include electronic health records, social media databases, anything to do with the internet essentially, but these were not designed for research. So design data typically have a high level of detail, they're older, and they're ready to use, well, more or less. In contrast, organic data have a variable level of detail, they're newer, and they're not readily usable. In other words, they're unstructured, they're unlabeled. They would take a lot of work, if you were to do it the traditional way, to be able to use them in any form of analysis. Even if there's these differences, there's also a lot of really important commonalities. Using either designed or organic data, there's a lot of legal concerns. There's ethical and consent concerns. There's access fees. There's a great demand for technical expertise, and additionally, a time investment is required. So either way you approach an analysis using designed or organic data, there's still a lot of work to be done and a lot of considerations. So today we're going to take a closer look at the example of electronic health records in obesity research. Now let's just remind ourselves that EHRs are the digital versions of patients' medical histories maintained by healthcare providers to support the diagnosis, treatment, and care coordination. Electronic health records are big data. The databases include repeated contacts for individuals sometimes from years to actually across their entire life course. A key thing about EHRs is their quality depends on how the information was recorded. And this is also inclusive of ethical considerations. Let's also remind ourselves that EHRs are organic data. So this makes it incredibly critical to remember that they were not specifically designed for research. Why am I emphasizing this point? Well, there's several cautionary notes to think about when we're using EHRs in obesity research. If we use them in a non-thoughtful manner, we're going to come up with reduced prediction accuracy. In other words, we're not going to achieve the target of an actionable insight for obesity prevention, treatment, or management. A really key consideration is the data quality. Oftentimes there's missing or inconsistent information recorded in EHRs, and the lack of this information when fed into the AI machinery can actually reduce prediction accuracy. Furthermore, there's considerations about inequity. So if you think about the data which appear in EHR, it may reflect healthcare disparities if certain people in the population are not being seen by a medical practice. Furthermore, there's a lot of bias potential here as well. This can come in the data themselves, as also just referred to with the inequity, but also from modeling choices. So machine learning, artificial intelligence, or deep learning, they're not free of assumptions and modeling choices. Furthermore, there's ethical considerations because in many cases the ethical and regulatory frameworks are lacking or ambiguous. They haven't necessarily caught up with the pace of development in this area. And finally, there are concerns about external validity of these findings. When you're dealing with AI, it heavily depends on the data being fed into the machinery. So if it's too reflective of one setting, and then also with these additional modeling choices and with the data itself, the accuracy of the predictions may not apply to another setting. So how do we overcome this? Well, in the case of obesity research and AI, multidisciplinary collaboration is critical. We need the input of the healthcare professionals. They are on the front line. They have the experience of actually filling in these electronic health records, and they understand what some of these codes may mean because they're not necessarily used in the way the artificial intelligence machinery may expect. Furthermore, we need the patient perspective because they are the ones whose data is being used in these different types of analyses, and they're also going to be the end users of the outcomes. Data scientists are obviously pivotal in this type of research. We need their skills, their technology, and their availability to run these advanced analyses. Furthermore, we need epidemiologists. We need the population health perspective and the understanding of how biases in data may impact upon our outcomes and the implementation. And furthermore, this is not at all inclusive of everybody. Other disciplines are also required. But I think it's incredibly important, particularly in the field of AI, with the rapid advances and the potential to really improve health, that we make sure that we're using multidisciplinary collaboration to ensure the outcomes are good and fit for purpose. There's great benefits and challenges for using AI in obesity research. Obviously, one benefit is it increases the pace of discovery from prevention to treatment. Yet we can never forget the challenge that these predictions are going to be only as good as the data they are based on. Another benefit is that AI allows us to gain insights from integration of diverse data, something that's been virtually impossible before. But nonetheless, when merging these types of data about individuals from genetics to their environment to their health records, there's a lot of unresolved ethical issues which must be considered. Another benefit is this will lead to improved clinical decision-making capabilities, but it will never become a replacement for skilled healthcare professionals. So the key takeaways from today: AI is a useful tool of promising developments rapidly occurring in the field of obesity research, but nonetheless, considerable and important challenges remain in data access, integration, and potentials for bias. I think it's an exciting time. Electronic health records and linkages are opening up new horizons for obesity research. But the real key takeaway from today is that multidisciplinary collaboration is critical if we are going to generate fair, ethical, meaningful, and adoptable approaches to the prevention, treatment, and management of the disease of obesity. Thank you for your attention.
Okay, very nice. The speaker is not here in person, but I think it was a great way to start this webinar. Very nice. So, and again, if you have questions, use the to do those. So I would like to go to the next speaker now. So he's online. Pleasure to introduce you to Dr. Nicholas Gambardella. I hope I said your last name correct. I mean, it's my terrible way to pronounce foreign names is already legendary. So he is the research director at the French National Center for Scientific Research and a member of the European Genomics Institute for Diabetes. So Nicholas is developing AI models to predict childhood obesity at birth using children's and parents' information. This is really excellent and very useful. So within the European project OBEClust, he is developing deep learning models to predict the risk of childhood obesity at birth for children and parents, from children and parents' biological and socioeconomic variables. So this is something that I think it's really of interest of everybody in this webinar, and I'd like to make a note that according to the count, we have passed 100 participants, which is really good. So Nicholas, thank you very much for being here today for this first OBEClust webinar, and the floor is all yours.
Thank you. So first, I would like to check that the sound is good. Can you hear me?
Yes, excellent.
Okay. And can you see my screen?
We can also see your screen.
Okay, perfect. So thanks for the invitation to present my work within the OBEClust European project. And thank you to Dr. Baker for the excellent introduction of AI in obesity research and its challenge and opportunities. So I'm part of Genodia, which is a research unit in Lille, part of the European Genomic Institute for Diabetes. And within this research unit, my group developed deep learning approaches to study various cardiometabolic diseases, such as type 2 diabetes, liver steatosis, obesity, etc. We use different type of AI approaches, and our aim is really to understand the diseases, predict the risk, diagnose the severity, and hopefully at some point improve the treatment. And today I will present one project dealing with the prediction of childhood obesity based on clinical and socioeconomic data and using a type of neural network called multi-layer perceptron. So as you probably all know, obesity is an epidemic that is ongoing consistently. At the moment, we think that 1/3 of children are overweight or obese, and no matter which geographical region in the world, and no matter what the income is for the parents. In Europe, all countries are affected. Northern, southern, eastern, western, and about 7 to 10% of European children now are obese, more than overweight. So we all know that obesity comes with many health consequences. And the important thing is that it comes with health consequences in children, physical consequences, but also psychological consequences, such as reduced self-esteem and depression and others. But also obesity in children translate into health problem in adults, irrespective of the obesity status of the adult. And of course, children obesity is the best predictor of obesity in adults. 80% of obese adults have been obese in childhood, while only 50% of obese are 80% of childhood obese child become adult obese, while only 50% of adult obese have been obese in childhood. So OBEClust is a European project which aims to fight children obesity and to maintain health in all over life, from childhood to adulthood. And our approach is to predict the risk, to tackle the obesity with precision medicine, to engage the people to participate, so not just the children but their parents, and eventually to prevent the occurrence of obesity. We rely on many cohorts from all over Europe. Today I will talk of one of the cohort, the Northern Finland birth cohort of 1986. And with those cohorts, we have access to a very large number of variables, with the proviso highlighted by Dr. Baker before. So personally, I'm using the Finn cohort, and one fortunate thing for Finns, but unfortunate for people just studying obesity, is that the Finn population is relatively healthy. So not many children are obese, but still at 7 years old, we have around 9% of kids who are obese, which is not negligible at all. If we do a principal component analysis, that is a procedure by which we look at the most variation in a cohort, we see that there are clearly different distribution of obese and non-obese children. Here, each point is a child. However, we don't have really defined clusters of children, which makes all simple approaches to predict obesity very challenging. And also a problem is it will make very hard to impute missing values from population, because those populations are very mixed. If we look at the correlation between obesity, the BMI at 7, the body mass index at 7, and various variables, some are clear. The BMI from the father and the BMI from the mother, the weight at birth. So the correlation is clear, it's super significant. However, as you can see, it's very noisy, which makes any prediction very hard. So the state of the art was developed by the lab of Philippe Frogel a decade ago, where they developed logistic regression to predict the risk of obesity, of childhood obesity, based on the maternal BMI, paternal BMI, the number of people in the household, the occupation of the mother, if the mother was smoking or not, and the birth weight. And so just to go further, I would like to introduce the notion of area under the curve. It's a graphical representation we use to evaluate the quality of a model. So basically, we can compute the true positive that are predicted obese children who are actually obese, the true negative predicted non-obese children who are actually non-obese, and false negative and false positive, which are false prediction for obese, non-obese and obese kids. And we can make this plot that you can see on the right. And in this plot, basically the diagonal means a random prediction, and that's 0.5 of the area of the square. And the perfect classifier will give us 1, okay? And so this the model from Anita Morandi in the lab of Philippe Frogel was showing area under the curve or roughly 0.7, and that's our goal. So we are using artificial neural networks to predict that. So an artificial neuron is basically the sum of two functions. The first function will take a weighted sum of the variable we use for the prediction. We add a bias, and then we will feed that to what we call an activation function that will produce an output. So if this activation function is what we call the logistic equation, effectively an artificial neuron is a logistic regression. But we'll use several of those neurons. But first of all, since one neuron is a regression, we can re-implement the Anita's Morandi's model in the network, train it with the thin cohort. And so we have a training set of 290 obese and 580 non-obese people, and we will use weighted, we will weight the loss function to correct for this imbalance, and we have test and validation set as well. And when we do that, we see we can actually improve slightly on Anita's score. She got 0.7, and we get 0.72, and the sensitivity, which is basically the number of obese people children we correctly predict, is roughly 64%. And so I trained 4 different models with 4 different subsets of the data, and that's what you can see on the bottom right. And this is a comparison of the weight of the scores of those models. In dark red, you have the obese, in yellow, the non-obese. So, of course, here I have only 1 neuron, so the scores are very, very close. But we can improve on that. So it's a long story. I explored extensively different architecture, different type of activation, everything. And I ended up with a small model, fairly small, only 7 neurons compared to ChatGPT, who has hundreds of billions, actually. But with this small neural network, we can actually improve slightly on the prediction, but not a lot. The accuracy improve a little bit, but the sensitivity, the number of obese kids we can predict, increases. So now that was with the variables used by Anita, but can we improve on that using more variables from the data set? Because this data set is very rich. So we explored various possibilities, and at the end, we came up with a model that, in addition to Anita's model, took into account the gender, the weight gained by the mother during the gestation, the consumption of alcohol from mother and father, the education from mother and father, and the occupation from mother and father. So the education is based on the four levels that are derived from the international classification for education. And again, I can train this model, and we reach now an accuracy of 0.74, which is much better than the initial model, and the sensitivity reach 70%. So as you can see, the different models scores are much less correlated. So some models are better to predict some kids, some models are better to predict other kids. This is why we have to train several models and then combine the results at the end. it's important to say that the results on the validation set and the entire set are slightly different, and it turns out that the Anita's model kind of perform better on the validation set. So the figure on the right shows the prediction on the entire data set. In brown is Anita's model, and in red is the mean score for my model. And we have about 7%, we are 7% better for the accuracy of the prediction, but most importantly, now we have a sensitivity that is better than 70%. And that brings me to a problem, a discussion that we have to have as researchers and practitioners for the prediction of obesity. So here, I show you the correlation between the model predictions, so the means of model scores, and the actual BMI at 7. Yeah, the correlation is perfectly significant. So we are predicting quite well, but we still have a lot of false positive and a lot of false negative. So as I said before, the false negative are the people who are predicting non-obese and are actually obese. So it's a failure to duty, right? So we fail to predict those kids. And we could think, well, we have to predict as many kids as we want to have the highest sensitivity. But if we do that, we have lots of false positive. Kids we predict will be obese, and they turn out non-obese. And we are overzealous there, and there is a risk of stigmatization. So that's not an easy decision to make, and an easy decision to discussion to have. And on that point, I will end up my presentation, and thanks my group, the whole Egenodia people involved in the research and helping me, and other OBEClust members involved in this research. Thank you.
Thank you very much. Again, another great talk, and it gave a very nice idea of what can be done to predict the risk of childhood obesity, and of course is a long-lasting struggle, not only to guess but to prevent. So we have questions and answers at the end. Myself, I may have one as well. So let's move to the next speaker, Dr. Silvia Sabatini. So thank you very much. So she's actually working in one of our PAGRA partners at the National Research Council in Italy. She's not related with PAGRA, but she's doing work that we and other projects hopefully can use. So she's a researcher at the Institute of Clinical Physiology at the NRC in Italy. As I said, she has worked in the development of AI models for phenotyping metabolic diseases, such as obesity, metabolism-associated steatotic liver disease, and type 2 diabetes. And as I said, she's working in the labs, in this case, Dr. Amalia Gastaldelli, who is a partner of PAGRA project. So Silvia, thank you very much for attending this webinar and for presenting your talk.
Thank you for the nice introduction. Can you hear me?
Yes.
Okay.
And we can see your slides, although they are not in presentation. They are now in presentation.
Okay. Okay, so good morning to everyone. So as Nicolas has already mentioned, we know that the uprising prevalence in obesity is a worldwide phenomenon, and in both adults and children. And this increased incidence parallels the incidence and the burden on the healthcare systems of other metabolic diseases like type 2 diabetes, MASLD, that is metabolic dysfunction associated steatotic liver disease, dyslipidemia, hypertension, and etc. And okay, so we know also that metabolic diseases are complex, multifactorial conditions that are often coexisting. And here you can see in this picture a small a link between between some of the systems that are involved and all the possible risk factors that contribute to the onset of the disease. And this complexity make precision medicine and implementing precision medicine strategies way more important, because a deeper understanding of the heterogeneity of these diseases may benefit their care and management. So in this context, artificial intelligence can be useful, and because it can offer innovative tools to improve our understanding of the diseases. And this, as has been said in the previous talks, this can be done by improving the diagnosis, the stratification, and also the risk prediction and prognosis. And this could be done by integrating different data, easily available data like clinical variables, but also imaging data, omics data, and both retrospective, longitudinal, and cross-sectional data. In this talk, I would like to explore the stratification, which is the identification of important subgroups and different that explain different aspects of the disease. And this is usually done by unsupervised learning. So in recent years, several studies has been published to explore and identify these clinically informative subphenotypes. And the idea is to move from the complexity of and the continuum of the metabolic phenotype to the identification of different disease component and individual's risk. And a very important work for diabetes is the one from Alquist and colleagues that have proposed a refined classification for diabetes by using easily available clinical variables. And this has been done with unsupervised learning. So this is the classical classification of diabetes. And this is the novel classification that Alquist proposed, in which we see that there is a better grain of the disease. And these clusters were associated with different clinical characteristics in terms of glucose metabolism, BMI, age, insulin sensitivity, and resistance. And this was also importantly associated with the different outcomes. So we have that individuals in different clusters have a higher incidence in time to develop a chronic kidney disease or to have a coronary events. And this could be really useful for taking a medical decision. In another work that we published, we identified different subgroups of individuals at high risk of developing diabetes that responded differently to lifestyle intervention in terms of glucose tolerance. And this is another example of how this kind of modeling can be used to better direct the type of intervention that people should undergo. In muscle D, so metabolic associated dysfunction, steatotic liver disease, 2 recent studies have been proposed that use the same approach that I shown for the diabetes, the work of Alquist. And in the first one, we have a definition of 5 clusters with different cardiometabolic characteristics that were associated with a different incidence over time of type 2 diabetes and coronary events. In another very recent work from Raverdi and colleagues, they identified 2 groups of 2 different muscle D. One that is more metabolically driven by metabolic alteration, and another one that is liver specific. And they show that the incidence of chronic liver disease, but cardiovascular disease and also type 2 diabetes was very different in these two groups of muscle D. And lastly, another recent work has been done for the identification of phenotypes, different phenotypes of obesity. And this has been done with a more a slightly more complex algorithm, because they leverage, Coral and colleagues leverage the observed discordance between the clinical biomarkers and what is expected given their BMI. And what they found was that there was several clusters that were associated with distinct clinical characteristics, for example, liver-related, inflammation-related, alteration of glucose and lipid metabolism, and that was associated with a different risk of developing type 2 diabetes and cardiovascular events. And so even in this case, and even if more research should be done, this stratification techniques has been applied to obesity as well. So to conclude, we show that artificial intelligence could be a powerful tool to explore metabolic diseases heterogeneity, and that unsupervised learning has been successfully applied for the identification of subphenotypes that are associated with different disease components, but also risks and comorbidities. And this is important because these findings may have the potential to improve the prediction of clinical trajectories and maybe inform precision medicine approaches. Thank you.
Thank you very much, Sylvia. Very nice with clear uses in predicting the outcomes of those metabolic diseases. So please stay, because we have a question and answer at the end. So without further delay, we are going to move to the next speaker, Andreas Vezakis. So member of the coordinating team for the BioStreams project, is a biomedical engineering researcher with a master's in engineering and currently pursuing a PhD focused on applying machine learning to biomedical sciences. So Andreas, thank you very much also for being present this first OBEClust webinar.
Thank you for inviting me. I suppose you can hear me.
Yes.
Let me start the presentation. You can see, can you see my screen?
Perfect. Yes, perfect.
Okay, great. Okay, I will be talking to you about the requirements for leveraging AI for childhood obesity interventions. I would like to thank Professors Anastasios Doulamis and Dimitrios Kalogeras for their help with creating this presentation. First of all, let's talk a bit about the problem of obesity that modern society is facing. In 2021, 493 million children and adolescents worldwide were overweight or obese, and that number has tripled since 1990. And it is actually expected to skyrocket by 2050, with 1 in 3 children and adolescents being obese. Countries such as the United States, China, India, and Egypt are expected to have the largest number of obese children by 2050. Of course, these health conditions comes with numerous implications that make the everyday life of children more difficult. There are non-communicable diseases such as diabetes, of course, cancer, respiratory issues, mental health challenges like depressions. There are orthopedic problems because excess weight places stress on joints, causing pain and increasing the risk of injuries in areas like the hips, knees, and back. Gallstones. Obese children are more likely to develop gallstones due to their metabolic changes. Cardiovascular problems. Those children are at higher risk for high blood pressure, high cholesterol, which can lead to heart disease or even stroke later in their life. Therefore, early detection, prevention, and long-term management strategies are crucial to mitigate this healthcare burden. And in order to have effective intervention, it is required to involve healthcare providers educators, parents, and of course, innovate technologies like artificial intelligence. We mentioned early detection, prevention, and long-term management, which is exactly what AI can help with and has helped with. For early detection and prevention, there are systems that integrate electronic medical records with computerized decision support systems. For example, a model analyzes 167 characteristics from the first 2 years of life to predict childhood obesity development, allowing for much earlier intervention than traditional methods. Machine learning models produce more precise obesity predictions than statistical modeling and can identify complex variables influencing obesity risks, from pocket money and mobile phone usage to feeding style and sleeping quality. For long-term management now, there are AI systems like food predictions, which analyze data and recommend meals that satisfy the daily calorie and nutrition requirements, without, of course, exceeding the daily limits. From those models that I briefly described, we can see that in order to be created with a high enough accuracy, a lot of data is needed. That is why we say that AI models are only as good as the data they learn from. With good data, we can have an effective risk prediction, personalization of interventions, and monitoring over time. But without the diverse high-quality data, AI can misinterpret that info and even reinforce biases. There are numerous of examples of AI reinforcing biases, but specifically for our case, there is a case study of a model trained on wearable data predicting obesity risk with an accuracy of 85%, but it failed in rural populations due to lack of training data from that group. Now, there are a lot of data types that we can collect and use for our models to train with. There are individual health data like the age, the gender of the child. There are behavioral data like eating habit, physical activity, how much time they use their phone, environmental data, where they live, how much access they have to healthy foods, etc. Their medical history, psychological data, meaning their mental health, longitudinal data, how the child responded to previous programs or treatments. Lastly, socioeconomic and financial data, which could be included in the environmental data, but because of their importance, I've decided to separate them. It is easy to talk about data, but in reality, the collection of correct data is probably the biggest difficulty for AI, and it is where medical sciences lag behind other fields. And therefore, in obesity, the current AI models that are used have a lot of more capabilities if more data are collected. The challenges that we are faced with are, of course, privacy and ethics, because children's data are sensitive and they must require strict consent protocols. One more challenge is data fragmentation, meaning a lot of data may be collected, but they are not shared between the collectors. The one we discussed in the previous slide is the lack of representation from under-resourced or minority communities, which can skew the results and create bias. Standardization, different schools or clinic, they may collect data, but they collect them differently. And even though they might be the same, they are not accepted by the AI model. For example, notes or PDF are unstructured and the model doesn't know how to handle them. And lastly, because for the most part, we are talking about supervised learning, the data need to be labeled, which requires an expert to label the data, and it is very time consuming. Lastly, I'm going to mention two systems that use AI. No, I'm sorry. The requirements to use AI is not only about data. The algorithms and the software require a lot of knowledge to be implemented. And there is also a huge need of computational power and storage to process those algorithms and store all the medical data and models. Now I'm going to mention two systems that use AI. The first one is the CHICA system. It is a system that identifies medical risks early. Based on input data and electronic health records, it flags potential health or developmental concerns like obesity, and it also supports clinicians. It generates a tailored recommendations and alerts for physicians at the point of care, helping them guide decision making. Also, the MinStop application, which promotes healthy lifestyles in young children, typically aged between 2 to 6 years old, with the goal of preventing childhood obesity. Those systems faced a lot of obstacles. They faced a lot of data limitations. The earlier models relied on more expensive and less available genetic data. The CHICA system had to overcome this by collecting electronic health record data instead. There was also a need to translate and customize for priority population, such as immigrant children who are less likely to participate in population-based health interventions. This demonstrates the challenges in reaching diverse populations. And there were also technical requirements that needed a lot of attention. Multiple machine learning algorithms, such as decision trees, random forest, and Bayesian networks, they must be evaluated using the same dataset and with performance analysis to determine which algorithm provides the highest prediction accuracy. Of course, there are many more algorithms, and the experts must have the knowledge which ones to choose and how to use them. Moreover, the systems must be designed for real-world settings beyond control research environments, with interactive elements that will maintain user interest and participation over time. Lastly, before widespread deployment, the system should be thoroughly tested and the system should be thoroughly tested in primary healthcare settings. For the last slide, I would like to mention PREVENT, which is a collaborative EU funding action that Professors Anastasios Doulamis and Dimitros Kalogeras are representing, and it aims to improve and upscale primary prevention of cancer by addressing childhood obesity. Through diligent implementation research and comprehensive approach, PREVENT aims to lay the foundation for a future where healthier lifestyles and brighter tomorrows await every child. That's all from me. Thank you for your attention.
Thank you. Thank you very much. And again, stay around because we have a question and answer at the end. So we'll move forward. Now we actually have Peter Atanasov from Amaris Consulting and share of the eProbes work package on multiomics, bioinformatics, and artificial intelligence. And alongside him, we have also Alex Bravo, machine learning and natural language processing researcher and developer at Amaris. So now we have two, as we say, two for the price of one. Thank you very much.
Excellent. Thanks for the kind introduction. I don't know who's the free one. Maybe I'm the one for free. So hi everyone. It's a pleasure to be here. My name is Peter. I think the importance of preventing childhood obesity is well established by now. I think we've heard a lot of statistics today on the level of prevalence of obesity in children and adolescents. I think we've heard a little bit about also the burden that these people have, about the burden that the families have, and of course the burden that condition poses on public health institutions. So clearly preventing it or intervening at the right time in order to change the trajectory of those suffering with obesity is important, both from a humanistic standpoint as well as from an economic standpoint, and clearly a very high item on the public health prevention list, so to speak. And I think we've also heard the fact that it's pretty challenging to predict obesity. I think, you know, if we were able to do that in a way that is translatable to clinical practice, we would have done it by now. I had a young daughter very recently, and yes, we still use in clinical practice the percentage, the percentile in which the birth weight is, and kind of look at whether somebody is going to be likely obese or not, just based off of that. So although we may be talking about a very technical, high-end predictions here, what happens in clinical practice tends to be still rather different. And you know, it will take a little bit of time until that trickles down, I suppose. But we've talked about complexity in preventing obesity, and of course, why that complexity is there is because of the fact that you have many different things that influence your risk. We talked about genetics. We know that some children will inherit genes that are more susceptible, that makes them more susceptible for their either appetite regulation, also metabolism. Alex, it's okay. We can stay on the slide. We don't need to change. Okay. Yeah, it's just a long introduction, so to speak. So we know that there are genetics that affect appetite regulation, metabolism. We know that there's also a lot of research now into polygenic risk scores, but we know also that does not explain your trajectory, what happens to you in the future when it happens, and how exactly it will affect you. We know that there is also environmental factors. We've talked about physical environment, also social environment, the role of parents and parents' attitudes towards foods, the parenting style, whether the parent feels that the child is overweight or not can also have an impact on their development. There's also the behavior of the child itself. So dietary intake, energy intake, physical activity, sleep time, screen time. I think, you know, we can go on for a very, very long time here. And the thing is that these also risks are not probably the same over time. They probably change. The interaction between them changes as well. And traditionally speaking, you know, this is why it's complex to predict obesity, and this is why sometimes simpler tools that we use today in current practice are somehow, let's say, not too accurate, but they're being used because they're simple. Today we are at a place where we could potentially start bringing that complexity in a little bit more and try, at least within the research setting initially, to move away from simple linear heuristic risk charts and regression models to something that is a little bit more encompassing, and see whether we can model it more accurately. And as we've heard today several times, AI is a pretty and machine learning in particular is a pretty good candidate to kind of unravel that complexity with nonlinear data patterns and make it more possible to predict obesity compared to perhaps simpler statistical models. It is because it comes with specific advantages regarding handling of you know, high-dimensional data with multiple variables, capturing the nonlinear relationships between the different variables at different points in time, capturing not only the relationships between the various factors of the child, but also parents and also maybe variables that get introduced a bit later in life. And of course, to recognize hidden factors that we're not able to already see for some reason, maybe maternal education. You know, it comes down to also the data that you give the AI, as we've heard in the first and also last presentations. I think AI can also help with personalization. We've spoken a little bit about that as well. And that could be helpful to then make sure that you have a more kind of personalized prevention approach. If we think that certain things may work for one type of children, then clearly, you know, trying to administer those earlier will be more effective. We've talked about the important caveat. It doesn't mean that just because AI can do it, it will happen. It means that we need to have very good quality data, and what that means has been covered, I think, in the previous presentations, talking about structure, representation, lack of biases, diversity of the data, the velocity, etc. So there's a lot of things that depend, and that they are almost the more difficult part, right? I think if you speak to any data scientist, any AI researcher, it will tell you that it's all about the data. So data is pretty important. And on that note, I wanted to just tell you a little bit about where we are. So we're part of the EPROBES consortium. So if we move to the next slides, Alex, it will tell you a little bit about what we're trying to do. So the slide after. Within our work stream, we are trying to use multi-omic data, and also, so Alex, next slide. And data from more classical cohorts to estimate the risk of early obesity in children. That's what we are trying to do. We are still in the process, so I won't be able to share results with you today. But what I can show you is one part which we said is important, that's about the data sources. On the next slide, and then the slide after, we have just a list of the type of cohorts that not necessarily will be used for our model training, but are part of the EPROBES consortium. So this one, and then the one after. So that it hopefully what that tells you is that we do have a lot of data and diversity of it to train a model. And with that, I will hand over to Alex, who will speak a bit about what AI models in obesity also have shown, as we've done quite a bit of research into the topic too. Thank you.
Okay, thank you, Peter. I think you can hear me well. Can you hear me?
Yeah.
Okay, thank you. So yes, I will continue the presentation. As we have commented in this webinar, obesity is a very complex disease. It is not caused by just one thing. It involves genetics, epigenetics, behavior, environment, and even physiological and socioeconomic factors. Unimportant events can happen very early in life, even before birth. In EPROBES, we work with very different cohorts from different countries, collecting many types of data, as Peter mentioned, clinical, mental health, behavior, diet, and multiomics. And the artificial intelligence here can really help us because it can handle all this complexity, this kind of different kinds of data. And also I can find hidden patterns in very large and messy data that humans might miss. It can also combine different types of information and predict how obesity might develop over time. We did a systematic literature review based on artificial intelligence, machine learning, and obesity in child. And from our systematic review, we saw that in terms of machine learning, random forest, gradient boost, and decision trees are the most used machine learning methods. Why? Because they are very good and handling nonlinear relationships. They work with many variables. They are robust, even if the data has outliers, and they are easier to interpret compared to very complex models like deep learning or complex neural networks. The most common variables used to predict obesity are simple but powerful: sex, parental BMI, education, birth weight, sleep, and income. These are easy to collect, and they show strong connections to obesity risk in many studies. Also, so we also found that most models use one type of data at a time. For example, only clinical data or only omics data instead of mixing everything. This makes sense because different types of data need different processings. The predictors for obesity include biological markers like gene methylations and leptin levels, physiological factors like emotional eating, and even good microbiota. The outcomes predicted are things like BMI, body fat percentage, waist circumference, and insulin resistance. So the key takeaway is there is not a universal model. Each cohort and each type of data might need its own model. Because our cohorts are so different countries, different data collected, we cannot just build one model for all of them. Instead, we need to create models adapted to each cohort characteristics, different variables, different type of missing data, different pre-processings, different risk profiles. And later, maybe we can combine them or find common patterns. But first, respecting the diversity will help us build much better, more accurate predictions models. The plan for this project is to first build models for each cohort individually. This way we can respect the differences and maximize the performance. And later we can explore combining them through methods like transfer learning or ensemble models. AI will help us predict obesity risk over time, find early warning signs like biomarkers, and design personalized prevention strategies for children and families. And in the last part, I want to talk about the generative AI, because in the last years, generative AI like GPT has become very powerful. However, alone, these models can make mistakes. They can hallucinate or miss important new data. To solve this, we can introduce the RAG system, the retrieval augmented generation. It means that the AI can connect to real databases, to real data, like our studies, our cohort results, our data, and provide answers that are accurate, updated, and explainable. For example, we could ask to the AI what are the main risk factors for obesity in the spine cohort, and it will find to the real evidence, not just invent something. So this approach could really help researchers and clinicians to access knowledge quickly and safely. And also, we try to integrate machine learning in order to interact with experts and familiars with the models we will build for this project, using the natural language as the input data, and also the results or the response of our models. So thank you for your attention, and if you have any questions, you can write in the chat, and maybe later we can answer the questions.
Thank you very much to both of you, and that was what exactly I was about to tell, so that if you have questions, please don't be shy and write them in the Q&A box. Please. We have 2 questions right now, but we need more. Our speakers need to have many questions to answer, please. So we're going to move to our final speaker. So it's my pleasure to introduce you to Dr. Stravola Mojiakaku. I hope I really said your name correctly. She's an associate professor at the Faculty of Medicine, University of Bern. She's currently leading the artificial intelligence in the Health and Nutrition Laboratory at the Hertog Center. Her research interests include AI, of course, machine learning, computer vision, and their application in prevention, diagnosis, prognosis, and treatment personalization of acute and chronic diseases. So she's collaborating currently with the Better For You project. So also, thank you very much for attending this webinar and giving your presentation. And again, apologies if I didn't say your name correctly.
Thank you so much for inviting me to be present today, and thank you also for the very nice introduction, and you pronounce my name absolutely correctly. And it's always challenging to have the last presentation, especially if the last presentation is before the lunch break. So I will try to speed up. And I'm here I'm speaking from Switzerland. I'm representing the AI in Health and Nutrition Laboratory of the University of Bern. The group was established in 2008, and the primary work is in the domain of AI for diagnosis, treatment, personalization of acute and non-communicable diseases. And we work in a spectrum of diseases from nutrition, diabetes, obesity, to inflammation-related diseases like the fibrosis. And I go straight to the Better For You project, in which we are trying to develop innovation for the prevention of obesity by integrating expertise, domain expertise knowledge, along with AI, plus information coming from different wearables that the participants, all of us, we are wearing during our everyday life. And using this information, we try to apply AI in order to identify insights from lifestyle, environmental, clinical, and biological factors in order to identify those that have a more important per person role in the development of obesity, and consequently to develop strategies that support the experts to provide interventions able, hopefully, to manage obesity along the lifespan of the person. So we have multimodal data. We try to analyze this information in order to understand the etiology and provide interventions, suggestions at personalized level in order to better manage the disease. In order to accomplish this work, we are 28 partners from 21 countries. The partners, some of us are coming from academia. Some of us, we have expertise in AI, some others in computer science, some in healthcare domain. The group is supported by the public and private sector. We have organizations of obesity involved in the consortium. So I think it is, we are 28 partners covering all the different stakeholders under the umbrella of obesity. And we work in this domain because obesity as the metabolic diseases in general, it seems that they are driving out of control despite the measures that are taken nowadays by all the different governments. The numbers and the statistics have a clear indication, that the population of people suffering from metabolic disease will increase in the near future. So we need to do something, and we need to do something beyond the currently established methods. And the same holds for the rest of the projects that have been proposed, that have been presented today. And the Better For You, we used, or we are planning to use cohorts, already established cohorts from more than 1 million people worldwide. These cohorts, the data from this cohort will be analyzed together with domain expertise. And based on this data and knowledge, we are planning to create a graph. The graph will be used as a basis for the reasoning in order to develop interventions that will support people to manage the condition. We will have a pilot study which will allow us to use the data to fine-tune the graph, and this fine-tuned graph will be used later in a multi-center study. And of course, we will assess the performance of this entire effort. And let's come to AI. It has been, why AI, and why the particular method that we are using in Better For You. So AI is, as it was already mentioned, is a rather broad spectrum of methodologies dominated by machine learning. So the methods that are use data in order to conclude to an output. And in machine learning, we have the deep learning, the super famous branch of algorithms that are used in order to analyze the big data. We have reinforcement learning, another category of machine learning that allows us to take decisions. We have computer vision, which is a branch of algorithms that come out from the combined use of image processing along with machine learning. We have the natural language processing that exists since many, many decades now, but along with deep learning allowed the development of the large language models. You can mention ChatGPT, Mistral, Llama, etc. And slowly, we have the development of another domain, which is inspired by the graph theory and causal inference. So I would say more statistics, and discrete mathematics, along with machine learning, which concludes the domain of causal machine learning. This subdomain of machine learning, or AI, seems to be a super powerful group of algorithmic approaches that allows us to model the cause-effect relationship, to make what-if predictions, and in general, to support the smarter decision-making process. And let's come to what we are doing in the Better for You. In the Better for You, we have a system, a static description of the system, which is resulted from the established knowledge. So now we take the data that is collected from the different cohorts. We have the experts that provide the most useful knowledge, and along with the AI technologies, we try to train a model using both the data and the knowledge, the established knowledge, in order to fine-tune and personalize the graph that is organizing whatever we know about obesity. So effectively, the model is coming into the game in order to say to us, to the healthcare professionals, if a causality between two nodes exists or not. And with this way, having trained this model, we have a complete graph which represent the role of the different parameters for each particular person. And how it works. So here we have at the center, we have the graph. We have the background knowledge which support us to create, to define the causality. Then we have the data. Then we have a module for the inference, and then we have the recommendations. And because, as I said before, we have data coming from 1 million people, which means that we have data that are sitting in different silos, we needed to apply it, and of course, its institute does not want to share the data. We had to find more intelligent way to analyze this information. And that's why we are proceeding to a hybrid scheme of federated learning and local learning, and central learning. So, as I mentioned, we have multiple sources of heterogeneous data. The vast majority of them have a lot of concerns about sharing the data. That's why we're using federated learning approach, and in this effort, we are supported by NVIDIA. And the federated learning approach, what it allows us is that we have a global model. The model goes to the local sites. It is trained there, and the weights, not the data, the weights come back to the central server. So effectively, instead of transferring the data, of sharing the data, we transfer the model. The model is trained locally, and the weights are going centrally back to update the master model. And this way, the data do not transfer, do not go from one place to the other, and this ensures privacy and security. But of course, this makes things a little bit more complex because all the standard algorithmic approaches, they have to be modified in order to allow this the development of this federated scheme. And as a use case, as a demo, to start playing with this concept, we use the biobank from the Harkopio University of Athens, which is composed by 14K samples from people living in Greece. And as you can imagine, because this biobank contains a lot of different data, we had more than 2,000. We had to exclude more than 2,000 samples because of missing values. And with the rest of the data set has been splitted into 3 groups of set, each of them representing one pilot site. So one effectively private data. So the next step was to develop the causal graph. And in order to develop a global causal graph, that supports all the data. This is in theory, but we started using an optimization-based algorithm, which is known as Nautier's algorithm, in order to create this causal graph. And in order to incorporate the background knowledge, we have asked professionals to give us feedback on what it is important, what kind of relationship between the nodes is important to be considered. Because as you can imagine, if you do not have this kind of rules, which effectively represent how the information flows and what influence the other node, the complexity of the problem can be extremely high, and there is a lot of randomness in the way in which the nodes are connected with each other. And once we applied these methodologies in the data coming from HUA, plus along with the expertise from the healthcare professionals, we conclude this simple graph. Of course, this will be bigger and this will be developed further during the years, but this is how we started, and you see the nodes and how they are connected. And the last part of this pipeline is the causal inference. Effectively, it is the mechanism that uses the information from the graph in order to identify how the different interventionals that can be applied and what the effect of each interventional will be to the person. So this is as for the analysis of the heterogeneous data. Of course, from one side, we have to understand the etiology, and we aim to use these causal machine learning approaches to fulfill this task. But from the other side, we need to find ways to monitor the lifestyle of a person. And to this end, in the Better For You project, we use a technology that is already used in another project funded by Horizon Europe, the project Melissa, in which we are using a system that allows the user to take picture of the food, and then through a number of steps that detect the food item, recognize them, and output the nutrition content in terms of calories, carb, protein, and fat, to register the food intake into the system. And this way we can capture information about the eating habits of the participants. In the Melissa project, we use this technology to support people with insulin-treated diabetes. In this project, we will use the same technology adapted not to have quantitative information, but qualitative information about the portion sizes that they are consuming during the day. And the system has already been validated in different studies. And here you can see a little bit of the studies that have been already conducted. And it supports all the different types of smartphones and take advantage from the different kind of sensor that each smartphones may have. And it is also localized. It's important to be mentioned that it is all localized to Switzerland, of course, to Denmark, Greece, Germany, and Netherlands, because of the needs that we have in the Melissa project. And it will be localized also in the countries that participate in the RCT trial for the Better For You project. And behind this Go Food system, we are creating a food knowledge graph in which the national food composition databases are supported by recipes, by information coming from Go Food, but also from other similar technologies in this domain, in order to develop, along with large language model, a system that is able to answer questions related to healthy eating habits and or to diets in order to prevent the onset of a disease. And the aim behind this is to develop a system that can not only be used for association between diet and disease, also or for dietary assessment purposes, and dietary recommendation, but also for safety and security, food security mechanisms. Can be used also as a part of smart appliances, for ingredient replacement, and so on. And with this slide, I would like to thank you. And of course, if you have questions, I'm more than happy to answer that. But you can also contact me or contact the Better For You project. Thank you.
Thank you very much for this excellent talk. And actually, one of the questions we have may be related with the app that you mentioned. So first of all, let me thank again all the speakers for the great presentations. I think it's covered a lot of ground on use of artificial intelligence in this field. So I think that the close to 100 participants gained a lot from these talks. So we have now 15 minutes, so we'll go until 12:50 roughly.
I can maybe answer. So the first question I already answered was about taking into account the ultra-processed food consumption, and that's indeed super interesting. And having the consumption of UPF by parents will be useful. Not by the kids, because we predict childhood obesity from birth. So at birth, the baby has not consumed any ultra-processed food so directly. Through the mother's milk would be another thing. But unfortunately, this information, I don't think this information is available in the cohort used by OBEClust. So thank you for this question, though. That was the first one. The second question for me, I think, was is using BMI at 7 the only measure is using BMI at 7 as the only measure an issue with these models? Have you tried other measures such as waist-hip ratio, etc.? So first of all, we do not predict directly BMI. It's not a regression model. We predict obesity as defined by the WHO. And of course, WHO used the BMI as a predictor. Actually, they use a corrected BMI, adjusted for gender, and etc. Why at 7? There are two answers, one rational, one practical. The rational is that 7 corresponds to the BMI rebound. So when you are born, your BMI actually decreases over the first year of life. You lose fat very quickly, and then at some point you start to gain fat again, and the rebound is around 6-7 years old. The practical reason is that it turns out in the FNBC 86 cohort, 7 years old is the age where we have the larger share of obese children, close to 9%. And to train models, we need as many subjects as we can. And at the other ages, the data set is even more unbalanced. So that's the practical answer.
Thanks for addressing this, Nicola. Much appreciated. Yeah, I think there is also like a direct follow-up to your question at the very end of the Q&A, if we would like to address that, unless...
Yes, we are using the paternal and maternal BMI. They are the most predictive variables. It's not completely deterministic. As you know, you have different types of obesity. You have the monogenic obesity, people who have a gene that will make them obese. So those people, they need to be treated with precision medicine. And this is completely hereditary. Then you have polygenic obesity, where you have hundreds of difference in your genomes, and that's much less predictive in particular because the mother and father have different genetic background. And then you have obesity that is mostly due to food, lack of sports, lifestyles, and this is heritable but not hereditary. It's not genetic, but it's heritable from your parents. But all taken together, the best predictors are always maternal and paternal BMI, because those cover everything, basically. They cover the genetic component and they cover the lifestyle components. So they're the basis of all the models I know of.
Thanks again. I continue to run this since I don't see Paulo coming back. We have also another couple of questions here about the adoption, basically, the adhesion to the tools in the health system. Yeah, anybody that would care to address this? I can quickly recap the questions for you. It's basically, do you anticipate good addition to this kind of tools in a health system where clinicians are more and more looking at the computer and less at the patient? And as a follow-up to this, what would be your preferred target to deliver these solutions? Would it be pediatricians or general clinicians or nurses? I think it's probably a bit broad, but probably connects with many many aspects of the projects that are in this call.
I think it is connected with many aspects related in general with adoption of AI in the domain of medicine, and especially if we go to the clinical setup. It's a super valid question, and I mean, by being an engineer within a faculty of medicine, I think that this is the topic, because from one side we can progress very much with algorithms and we can have fantastic solutions, but from the moment that cannot be integrated into the practice, they are lost. They are lost, and it is not an easy question to be answered, because in my opinion, there are a lot of parameters. There are parameters related to the process. So once you have a solution, it has to be integrated in a way that the process are not delayed, but they are accelerated. But in order to make this integration, the people need to be open to integrate the solution. And open means that they know what AI is, what they can expect from an AI solution, and they are not afraid from the technology. But in order to convince them for this, you need to train and to explain. So it's really, and by the end of the day, the healthcare system needs to understand that they have a profit. And profit means not only better management of the patient, better routines for the delivery of the hospitals, but also profit in terms of financial profit. So people are getting less sick. Physicians and health domain experts are more efficient. So there are also economical aspects. So in my opinion, it's not an easy to be answered question, and involves a lot of different levels, and it's not related only with the tools that we are creating for managing obesity. It is also related to the tools for diabetes, fibrosis, and whatever other application you can imagine in the healthcare sector.
Also, if I can add, there is also an ethical aspect to that, in the sense, so there are two aspects. One for the adoption. So what we can see in our cohorts is that well, some data people are reluctant to answer some questions, alcoholism, type of occupation, and so on and so forth. And we can see that the data set are way sparser when we reach a sensitive topic such as those. So we have to take that into account when we design our model. The second aspect is the inequality of access to health. to the healthcare system. So the model I presented today for obesity is on simple clinical data, but for liver steatosis, we have models that take into account biological markers. And those biological markers are pretty expensive to gather. And not all the hospitals can deploy some of the models. And of course, we reach, and it's well known that in areas where people are poor, in general, the healthcare system is poor as well. And we end up in a system that encourage, basically, our models may actually accentuate inequality. So that's something we have to keep in mind as well.
Thanks, everybody. I think in the meantime, we also had a couple of other questions. I have a question from the participant called Zainab that asks if tracking children physical activity level is considered, meaning sedentary lifestyle. Anybody that would address this directly?
Well, again, for our model, we predict the obesity at birth, so we cannot track any physical activity. But in many other cohorts, physical activity is also followed. I'm working personally on 2 cohorts for diabetes, where participants were activity monitors, wrist, basically GPS and accelerometers, and they wear that during 2 weeks every year, which allow to monitor fine activity. But within OBEClust, this is irrelevant. Maybe other participants can answer more precisely for their project.
There's no, I don't know if there is direct expertise involved during the call for the BioStream project on these aspects, but I will invite basically the participants to go and check out the website of the project, because there are some activities that are connected to the use of apps, which have the twofold objective to basically sort of track activities and also offer recommendations. But this is something that it's still in progress, and I'm not a direct expert, but I will invite you to refer to the website and even drop us a line there if interested. Okay, we have, well, we received also a message from Paulo, who unfortunately experienced a power cut, so he apologizes that he cannot jump in to moderate. And we have yet another question, which we would have time to address quickly, which is the following. In monogenic obesity, the pathological dysregulation of homeostatic hunger mechanism leads to hyperphagia. Is there any way AI can distinguish hyperphagia from eating disorders and help individuals to be addressed to genetic testing? It seems like it's a very loaded question, so but you still have time to address it. Please, anybody who would care or has an opinion in this subject can jump in. I would also add that if any of the participants will actually like to deliver a question vocally, please just raise your hands, and I will make you able to speak in case. Should it be easier than typing the question?
I mean, I can answer. We don't follow that in OBEClust, but in other projects of the unit, we deal with monogenic obesity, and surely just monitoring the food intake in terms of frequency and quantity would allow to do that, and surely AI could do it. But to be honest, I don't think we need AI for that. In case of monogenic obesity, the regular questionnaire by physician, by GP are generally sufficient, but that's just maybe a non-specialist opinion.
Well, if there is no additional question, then on behalf of the projects that organized this on behalf of the OBEClust group, and on behalf of Paulo, unfortunately, had to leave us. I would like to thank again all the speakers for taking part in this webinar today, for taking the time to talk about to us about what they are working on within the projects. I will invite again the participants to follow all of their channels and keep up to date with their activities, which are very interesting and relevant. And I would also like to state again, I've been answering this question in the Q&A chat throughout the webinar, that this webinar has been recorded, so the recording will be made readily available to the participants. We will probably send you a link via the T2 registration platform that you use to register. I think that's probably the easiest vehicle to get that to you. And it will be also transmitted to all the projects for their internal use, for their use in their channels. So without any further to do, thanks again, and I wish you a good rest of the day.